All right, so there is another method to find a resultant vector. That one is by using resolution of vectors. Now, for resolution of vectors, the key thing to know is that any vectors can actually be resolved into two mutually perpendicular vector components. Okay, the key thing to know first is that if you have any vector, it can always be resolved into two mutually perpendicular vector components. It can always be resolved into two components that are perpendicular to each other, such that if you combine these vector components again, you will get back the original vector. What do I mean by that is that if, say, you have a particular force, a vector here, a vector f, this particular vector can be resolved into two components that are perpendicular to each other, say fx and fy. Now, if you were to redraw these vectors from head to tail again, you will notice that if you draw vectors fx and fy from head to tail, they will actually give you back the resultant, which is actually the original f. Okay, these two are actually the components of this original vector. So if you combine these two again, you get back the original vector. It's kind of like the resultant here. Okay, now say we take an example now, a force F acting at the angle theta above the horizontal and angle alpha from the vertical. We are interested in resolving that vector into two perpendicular components. Okay, here the vector is this vector f here. We are resolving it to two perpendicular components, fx and fy. The thing we want to do here is that we want to express the vector components in terms of the angles and the original vector. So one of the key things about resolution of vectors is that you need to know how to find the expression for the components. So we first start off with this triangle, okay, which gives us this. All right, how do you get this triangle is mainly by shifting fy to this side so that it now forms a right angle triangle. Now, from here, you can work out a few relations based on your knowledge of sine and cos. If you remember last time in your maths, when you have a right angle triangle with sides A, B, and C, you would say that, okay, if this one is a right angle triangle with angle theta, you would say that cos theta is equals to the adjacent over the hypotenuse, where sine theta will be equals to the opposite over the hypotenuse. Now, if you apply this trigonometric functions here that you learn in maths over to this triangle, you can actually say that cos theta is equals to the adjacent side over the hypotenuse, which will in turn give us this. Fx is f cos theta. And then if you apply sine theta, which is the opposite side over the hypotenuse, which is actually fy over f here, we would get fy is f sine theta. Now, the common thing that some students tend to misunderstand is this. They have a tendency to always think that if it's the horizontal component, it's always cos. If it's the vertical component, it's always sine. This is actually not always true. It actually depends on how the angle is actually described in your question. What I mean by that is that if you look back at the center diagram here, you can actually get another triangle from this diagram, which is shown on the left. You can actually see this diagram. You can actually get another diagram, which is the one on the leftmost here. So this diagram, how do you get this diagram? It's actually obtained by you shifting fx to this side so that you now form another right angle triangle. Fy remains where it is, but fx, you shift it to this side so that it now forms a right angle triangle, so that when fx, fy are drawn from head to tail, you get back the original vector f. Now this time your angle is a bit different. It's no longer theta. It's actually alpha now. So if you want to find out what is the relation now, you do the same thing as before. This time you will say something like this. You will say that sine alpha is fx over f, giving you fx f sine alpha, whereas cos alpha is fy over f, giving you fy f cos alpha. So now you see it's a bit different now. Whereas previously fx was cos, now fx is sine. And then last time fy was sine, now fy is cos. They've actually switched places. So it won't necessarily be true to always assume that the horizontal component will always be cos or the vertical component will always be sine. It depends on how your angle was actually described to you. Now, there's actually a shortcut to finding out the expression for the components. You don't really need to like draw a triangle each time and then do the derivation like I've done here. There's a shortcut to it. The hint is from your definition of sine and cos. You learned that last time when you're talking about cos, you are always taking the adjacent side of the triangle. Whereas when you're talking about sine, you're always taking the opposite side of your triangle. So now you can apply this for resolution of vectors. Whenever you want to express a component in terms of the original vector and the angle given, you look at how the component is situated in relation to the angle. What do I mean by that is, if you just look back at the rightmost triangle here, you just look back at the rightmost triangle here, you see fx is actually adjacent to angle theta. So you will know the expression would actually be cos. But on the other hand, if you see fy is actually opposite to your angle theta. So it will actually be sine. Now, if you apply the same reasoning to the triangle here, you actually be getting the same conclusion. You actually be getting the same answer. You look at, say, now fx. Fx is opposite to angle alpha. So it will be sine. And then you look at fy. Fy is adjacent to angle alpha. So it therefore must be cos. This is actually the fastest way to find the expression for the components. You just look at where the component is with respect to the angle that you are interested in. If it's adjacent to the angle, it will always be cos. If it's opposite to the angle, it will always be a sine. Okay, so this is how you resolve your vector components in the first place. You need to know how to resolve these vector components before you can even move on to finding the resultant vectors in the example before this. Okay, so this one, okay, I will just erase this one. Can I just erase everything on the screen? Do you need to copy anything?
It's okay, I screenshotted it.
Okay, right, no worries. After the class, I will also still upload the recordings into Google Drive. You can actually refer back to the diagram from there later. Okay. All right, so let me just clear some of the drawings and then let's just go to this. Now, how do you actually apply resolution of vectors to the examples before this? You still have the same example where you have vector A at 13 Newton horizontally and vector B at 15 Newton and the angle of 40 degrees to the horizontal. You're interested to find the resultant. Now, in general, when you want to find the resultant using resolution of vectors, the first thing you would normally do is this. You would normally resolve any diagonal vectors you see into two perpendicular components. The only diagonal vector that you see in this example is this one. So when you resolve it, it will be resolved to these two components here. This one, if I look at the horizontal component, you will notice that this is actually adjacent to the angle. So this one will actually be 50 cos 40. Whereas the vertical one, if you try to make it to complete, if you try to shift it around to complete a triangle, you will notice that this arrow shifted to this side will actually be opposite to the angle. So this one should actually be 50 sine 40. So you have now resolved the components of the vectors. You have resolved the vector to the components. Then the next thing you will do is this. You will actually sum up all the component vectors in their respective directions. What we mean by this is in the x and y direction, or the horizontal vertical direction, if it makes it simpler for you to understand. So now what you do is this. You find out the sum of the horizontal forces. Now recall that before this, I mentioned that whenever you want to add or subtract off vectors, you tend to set a sign convention, which tells you which direction is assumed to be positive. Since you see that majority of the forces here seem to be pointing towards the right, you will just say going towards the right as positive. So now, you sum up all the forces that you see are in the horizontal direction. The only forces in the horizontal direction is this one and this one. So what you do is that this one would be 30 plus with 50 cos 40, in turn giving you 68.3 Newton. And then you sum out the vertical components. You see that there's nothing, most of the only vector is pointing outwards, right? So you can actually just say that going outwards is positive. So here, when you look at the diagram, you will notice that vector A does not have a vertical component. It is just horizontal. Whereas vector B, there is a vertical component, which is this one. So the only vertical force here is just 50 sine 40, which in turn gives you 32.1 Newton. Okay, then after that, we will tell you, after you've done that, you apply Pythagoras theorem to find the resultant force magnitude and direction. Now, why do we say we can use Pythagoras theorem here? Now, it's because if you look back at the original diagram here with all the forces resolved, when I say sum of Fx forces being equals to 68.3 Newton, it can be represented as a horizontal line like this, where this is sum of Fx being equals to 68.3 Newton. This line here is actually this line and this line combined together already, giving you this. And then when you look at sum of Fy being 32.1 Newton, is actually can be represented as a single line like this, where it's 32.1 Newton. Now, if you rearrange sum of Fx and sum of Fy as vectors that are drawn from head to tail, it will look like this. Okay. Now from here, you notice that there's a gap. This gap is this portion here, okay? The length of this gap is actually going to give you your resultant. Now, same thing as before, since this one was your first point, and then this one being your last point, your direction is going to be here, okay, for going upwards. Now you see this one here, because the vectors were originally horizontal and vertical, perfectly horizontal, perfectly vertical in the x and y direction, they're going to be at right angles to each other. So this one is actually a right angle triangle now. So recall that earlier just now I told you, when you see vectors forming a right angle triangle, you actually can just straight away do a calculation using Pythagoras theorem. So over here, you see you having a right angle triangle where R is your hypotenuse. So over here, you can say that R is actually the square root of sum of fx squared plus sum of fy squared, which in turn will give me 68.3 square plus with 32.1 square, in the end giving me 75.5 Newton. And then now, if I want to find the angle, say this one is angle theta, you can actually use your triangle functions here. You can say that tangent theta is the opposite side over the adjacent side. So you get sum of fx, sum of fy over sum of fx, giving you theta as arctangent of 32.1 over 68.3. So eventually you get your final answer as 25.2 degrees. Okay. Now this would be your resultant and your angle calculated out. If you compare with the previous example where we say that you draw a scale vector diagram from head to tail, I will just draw a simple diagram here. You draw vector A, you drew vector B, and then you say that the resultant is here. This one was using scale vector diagram. We say that R here was 76 Newton, and then theta here was 25 degrees. This was using scale vector diagram. Okay. Now notice that that resultant you have here is actually this resultant you have here. Okay, you're actually getting the same thing. All right, but there's some slight variation in your answer here. You'll notice that this is 76 Newton, but you are getting 75.5 Newton. Whereas this one was 25 degrees, but you're getting 25.2 degrees. Now, in general, we would normally tell you that this one is actually more accurate in terms of the answer, where scale vector diagram is actually less accurate because it is subject to the accuracy in which you draw your lines. When you try to draw your scale vector diagrams, you'll notice that maybe your lines are not perfectly horizontal, or maybe when you want to draw the angle, when you want to draw your other vector, B at 40 degrees, how sure are you that when you start your vector B, you are exactly at the end of vector A? Sometimes people draw it slightly less or slightly more. So there's some inaccuracy there when you draw your lines. So when you have some inaccuracies in how you draw your line, you're going to have some inaccuracies in your answer also. So that's why we normally say that scale vector diagram is actually less accurate than using calculation with resolution of vectors. Okay, because this one here is very much subject to your accuracy in drawing your lines. Okay, but for scale vector diagram, because we already understand it's actually less accurate, normally in your marking scheme, they will give you a range of answers. They won't give you an exact answer in the marking scheme. They will normally give you a range of answers to take into account the inaccuracies of drawing your lines. Okay, so this is resolution of vectors. Then there's one last method that I should probably mention a bit to you, which is sine and cosine rule. Okay. Now sine and cosine rule is actually not formally covered in your syllabus. You would have three different methods to find a resultant vector. You would have scale vector diagram. You would have resolution of vectors. And then lastly, you would also have sine and cosine rule. Now, when you're doing your exam questions, only this two is required from your syllabus. Your marking scheme answers are always based on these two. Okay. Now, sine and cosine rule is actually not really formally covered in your syllabus. The syllabus doesn't require you to actually know this. But in your exams, if you show this method, they will still accept your answers nonetheless. Okay. So just bear in mind about the third method that I'm telling you, sine and cosine rule. It's okay to know, but if you don't know it, it's also fine because the syllabus doesn't require you to really know this. If you had used this method in your exams, they will still accept it. Okay, they do allow candidates to use this method too. Okay, so this one I'll just elaborate it briefly for you. So let's just go with this one. This one won't take a long time. Okay, now sine cosine rule, bear in mind that it's a bit limited because sine and cosine rule can only be used when there are three vectors involved. When there are three vectors involved, it means you can only use it for a triangle. Okay, sine and cosine rule is limited in the sense that it's only applicable if you have three vectors. In other words, a triangle. Okay, now before I go to that, in maths, you may have recalled that cosine rule and sine rule as these formulas here. If you have a triangle with sides A, B, and C, and then with corresponding angles of capital A, capital B, and capital C, cosine rule will tell you that A square is equals to B square plus C square minus 2BC cos A. Whereas sine rule will tell you that A over sine A is equals to B over sine B, and then equals to C over sine C. Okay, this is important to remember if you want to use sine and cosine rule. So when you want to use sine and cosine rule to find your resultant, if you are applying it to the example before this, where you had the force of 13 Newton horizontally, force of 15 Newton, and the angle of 40 degrees to the horizontal, what you first do is that you sketch the vectors from head to tail along with the corresponding resultant, but you don't need to draw it to scale. Okay. So you try to visualize how your diagram will look like. Your diagram will actually look something like this. This is your vector A at 13 Newton, vector B at 15 Newton, and then your resultant would be this one. Okay. Now, since you already said that this one is 40 degrees, the angle inside here would be 140 degrees. All right. Now, from here, you already have enough information to find R using cosine rule because you see, I want to find R. I know the angle opposite to it, and I know the other two sides. So this one, I can actually say using cosine rule, R square is equals to A square plus B square minus 2AB cos 140. Maybe rather than writing like this, I just submit the values first for you, so as not to cause any confusion. So it will be 30 square plus 50 square minus 230 times 50 cos 140. Your R would eventually give you 25.2. Sorry, not 25.2, 75.5 Newton. This one you will still get the same answer as before. Now, if you use sine rule, this one I will probably write it over here. Using sine rule, I can say that R over sine 140 is equals to B over sine theta. Now you only found the magnitude of your resultant here, but you haven't found the direction. Previously, when we talk about the direction, we always use this angle theta, right? So I apply sine rule here to find the angle. I'm using two different sides here. For the sine rule here, I'm using this pair, R and sine 140, and this pair, B and sine theta. I'm using these two pairs here. That's how I got this one here. So I know what is value of R. It is 75.5 over sine 140. And then B was 50 over sine theta. Once you try to solve and try to find out what is theta, theta would actually be equals to 25.2 degree. Okay, so you would have your magnitude and your angle now, which gives you your direction. So this method is using sine and cosine rule. This is another third method to find resultant. When you read your marking schemes as you do your past year, you might notice that sometimes they make mention there using sine and cosine rule. This is the method. Okay, but this one is the least popular method to use. Most of the time is scale vector diagram or resolution of vectors. All right, so this is one part of it. Now, there's still one part below here of the notes where I mentioned this to you. If you look at page 9, the last page, there's still some little stuff that I describe at the end, right? Here I mentioned to you your methods described only allow the magnitude and direction of resultant vector to be determined, but not the point where it acts. The methods that I mentioned here is actually your scale vector diagram and then resolution of vectors, and then lastly the sine and cosine rule. You use any one of these methods, you can find the magnitude, you can find the direction, but it won't really tell you the point where the resultant vector acts. Now, to give you an idea of what I mean by that, if you consider, say, a circle here, and then I tell you you have a force F1 acting here, and then you have a force F2 acting here. Now, if I were to ask you to find what is the resultant force, magnitude, and its direction, you could easily tell me that if I were to draw the vectors from head to tail, F1 followed by F2, my resultant would actually be this line here, given by this angle. The length of this arrow will give me my magnitude, and the angle here will give me its direction from the horizontal. But how do I know where this resultant is going to act? Is it going to be acting here, acting here, acting here, acting here, or acting here? You won't know, right? You only know the magnitude and you only know the general direction, but you don't know the point where it acts. Now, to find the point where it acts, you need to understand that vectors can be shifted along their line of action. the line of action of these two vectors is actually this line here. This dotted line, and this is what we mean by the line of action. Okay. So the point where the line of action intersects, that's the point where the resultant vector will act. If you look at the result, if you look at the lines here, this is actually the intersection of the two lines of action. Your resultant that you find here is actually going to be acting at this point, like this. This is where your FR is going to be acting. All right. So when finding the point where the resultant acts, just look at where the line of action intersects. That will give you your resultant point. Okay. Right. So with this, we've actually finished off the chapter already. So I'm just going to use the rest of the lesson here to go through some of the more challenging and difficult questions for you. You okay with that?
Okay.
All right. Okay, so we move on to some of the questions. Okay, last week I gave you some.
Yeah, I did those questions, but I have there was like 2 questions that I didn't know how to do.
Okay, right. So let me just go through them very quickly with you. You just stop me at the questions that you have problems with. Okay, so the first one I gave you was page 31, question 1. Okay, this is June 17, P23. Yeah, I also granted you access to Google Drive already. You could access the question. Could you access the work solutions?
I didn't check, but
Oh, you didn't check lah. You just haven't opened it before lah. Okay, right. No worries. Just let you know if you have problems with opening the solutions or to view the solutions, just let me know. Okay. Because I granted you access there, you should be able to see them. Okay, so we started off with page 31, question 1. So they told you right now, there are two forces with magnitudes of 5 Newton, 12 Newton acting at the same point on an object. Calculate the magnitude and resultant force of the forces acting in opposite directions or at right angles to each other. So if they're acting on the same point in opposite direction, it will look something like this. This is your point. You have two forces acting in opposite directions. So recall I told you that if you see the vectors are acting along the same line or parallel to each other, you can actually just add or subtract them from each other. In your case, since they are acting along the same line like this, you can just take one, subtract off the other. So it's just take 12 minus 5, giving you 7 Newton. But on the other hand, if you see them acting at non-parallel directions or in general just different directions, you cannot just simply subtract or add them. You have to use resolution of vectors, scale vector diagram, or sine and cosine rule. Okay, but I did mention that if you notice that they will form a right angle triangle, you can actually calculate them out directly. So over here, if your point was here, for example, your two forces would be this 5 Newton here and this 12 Newton here. Now they will form a right angle triangle, giving you this resultant. So it's actually the hypotenuse of a right angle triangle. So you can actually use Pythagoras theorem to solve. Square root of 5 squared plus 12 squared, giving you 13 Newton. Okay, so this is one part here. Then you have an object x that rests on a smooth horizontal surface. The horizontal forces act on x as shown. A force of 85 Newton is applied to the right. A force of 18 Newton is applied at an angle of 115 degrees to the direction of the 55 Newton. So now they ask you use resolution of forces or a scale vector diagram to show the magnitude of the resultant force on x is 65 Newtons. So over here, they give you two choices. You can use scale vector diagram or you can use resolution of forces. Now, in the case where you had used scale vector diagram, I mentioned to you to just use scale vector diagram first. Your answer for your resultant ought to be at 65 Newton. Okay, maybe you had used your scale as 1 centimeter to 10 Newton, but then, yeah, or your scale could be different. It won't matter. All right. But the important thing is that you need to draw your vectors from head to tail. So in my case, I drew the vectors from head to tail like this. This one, I believe, would be my 18 Newton force. This would be my 55 Newton force. I drew it from head to tail. So the gap is this line here. And then in my case, this was my first point. This one was my last point. So I know my direction is here. So I use my ruler. I noticed that my resultant is 6.5 centimeter. I take into account the scaling that I use. I should get 65 Newton. Now, you recall that I mentioned to you, scale vector diagram is actually not the most accurate because it is subject to the inaccuracies. It is subject to the accuracy of your line drawing. That's why they normally will give a range. Your marking scheme actually gave you this range. Okay, your answers could be anywhere between 64 to 66 Newton. Okay, as long as your answer is between this range, you will get your marks. All right, this is using scale vector diagram. But bear in mind that when you use scale vector diagram in your exam, you need to have your protector with you. All right. Okay, so this is scale vector diagram. Now, if you want to use resolution of forces, do you want to have some time to try resolution of forces? Or should I just go through it with you?
You can go through it.
Okay, I'll just go through it with you. Okay, now, so let me just clear off this one. So basically, this diagram is this one here, all right? Now, recall that I mentioned that what you tend to do is that you just resolve any diagonal vectors. If you refer back to the notes that I gave you, whenever you want to resolve, whenever you have any diagonal under resolution of vectors, what you do is that you will resolve any diagonal vectors. So in your case, your only diagonal vector is this one. You want to resolve it. So you get something like this and something like this. Okay. So this one, you need to first find out what is your angle here. Now, there are a few ways you can go about this. You can either find the angle here, or you can either find the angle here. Right? Depending on how you resolve and find your, depending on which angle you are using, your expression for your components will be slightly different. But in my case, I don't want to use this one here, the red one here. I want to use the blue one here. Now, in maths, you will know that if you have two parallel lines like this, if this one is a certain angle, this angle here would be 180 minus this angle here. Okay, this is what you learned in maths last time now. If you have two parallel lines and then there's something that cuts across them, if this is angle theta, the angle here would be 180 minus theta. So here you know that this is 115 degrees. That would mean that this angle here would be 180 minus 115. Giving you 65 degrees. Okay. Now then from here, you can find out the expression for your components. This horizontal component, notice that it's adjacent to your angle. So it will be a cos. It will be 18 cos 65. And then the other component, if you were to shift it to complete your triangle, you will notice it's actually opposite to your angle. So this one will be 18 sine 65. All right. So now you see how easy it is to do the resolution. As long as you see how the angle is situated with respect to your component, you'll be able to easily see whether it's cos or sine. Okay. Then after that, the second method I told you was that after you have resolved any non-diagonal vectors, what you would do is that you would actually sum up all the component vectors in the respective direction, either in the in both the x and y direction. So right now, if you look at this original diagram here, when you're talking about horizontal component of forces, there's only two. There's 55 and 18 cos 65. And say you put your sign convention as rightwards positive, this one will just be 15 plus with 18 cos 65. Okay. Did I do
So I have a question.
yeah, this one is 55. Sorry.
Yeah, I was like, how is it? I was like, where do you get 50?
Yeah, this one is only where did the 15 come from? There's a typo error here, sorry. This is 55. Okay, this is 55. There's a typo error here. So I was wondering where did the 15 come from? It's 55.
Am I wrong? I'm like, wait.
Yeah, I'm sorry, my mistake. Yeah, there's an error there. It's 55. Because 55 plus 18 cos 65 will give you this answer. Okay, so you're getting 62.61 Newton here. All right. Okay, then after that, you move on to the vertical component. Say going downwards is positive now because you see that majority of the forces, if any, are going downwards. So you just make it convenient for yourself. Downwards is positive. Okay. So as last week you mentioned to me, is upwards always positive? Is rightwards always positive? I mentioned to you, no. It actually depends on the context of the question. The easiest way for you to determine is to see where is the majority of the forces pointing to. That one you will take as your sign convention. So in your case, you see only the forces are always pointing downwards, so you just put downwards as positive. So now your vertical component of force is just 18 sine 65. So you get 16.31 Newton. Okay. So after you've done that, you can straight away use Pythagoras theorem. Now, whatever you have done here can actually be represented as another separate vector diagram. You see, sum of fx at 62.61 Newton is going to give you this diagram here, like this. This is your sum of fx. Okay, it's going towards the right because the sign convention is going towards the right. If it's positive, you're still in that direction. And then sum of fy is 16.3. Downwards is positive. So this one is positive. It's also pointing downwards then. So you try to draw it in such a way that they're from head to tail. So you get sum of fy here. Okay. Then after you've drawn it from head to tail, you will know that the gap is your resultant. And this one being your first point, and then this one being your last point, resultant is pointing here. Okay, so this is your FR. So it forms a right angle triangle. That's the reason why you can use Pythagoras theorem here. FR is square root of sum of fx squared plus sum of fy squared, giving you 64.7 Newton. Okay. This one would be how you get your answer. The question didn't ask you to find the direction, so you don't really need to bother about the direction. Here they say just magnitude of your resultant force. But I believe the second part asks you to determine the angle. Yeah, we'll go to that. Right. So this resultant here is actually the same as this resultant that you will find using scale vector diagram. Because I didn't draw my under this method, I did not draw the diagrams to scale. It doesn't seem similar, but by right, it is going to be similar. All right. Okay, then you go down to the next part of the question. They told you, find out the angle between the resultant force and the 55 Newton force. And they want you to find the angle between the resultant force and the 55 Newton force. Now, if you had used scale vector diagram, like the one above here, your 55 Newton force would be actually this one. This is your 55 Newton force, okay? The angle between your resultant force and your 55 Newton force, you can actually do something like this. You can extend the line, the horizontal line and the resultant line. This angle is what they want. Okay? You can actually just extend the two lines here like this and then find the angle. Or you could try and draw a horizontal line here and then just find the angle here like this. They are the same. Okay, no difference here. It's just a matter of how you want to proceed. If you had used direct measurement using scale vector diagram, you should be getting the angle as around 14.6. But again, the marking scheme gave you a choice of answers. As long as it is between 14 to 16 degrees is good. All right. Now, you can also try to calculate it out if you wanted to, your resultant. What you will do is that you use back the original triangle that you did just now, which was this one. Okay, your 55 Newton force was actually, if you refer back to the original diagram, the 55 Newton force is actually horizontal. It's actually a perfectly horizontal force, like this. So when they want you to find the angle between the resultant force and the 55 Newton force, it's actually enough if you just find this angle theta here. Okay? You just find this angle theta here between the resultant and a horizontal line here. That one will be giving you the angle itself. So as I mentioned, since this is a right angle triangle, use triangle, you can straight away use tangent here. Tangent theta here is equals to sum of Fy over sum of Fx, in the end giving you 14.6 degrees. That one will give you your answer. Okay? So this part is okay. Yeah. Because right now over my side is raining heavily, you can still hear my voice clearly, right?
Yes, okay.
Okay, all right. So if you can't hear my voice, just let me know. I'll probably have to speak a bit louder. Okay, so this one is okay. This one. Okay, so this one is done. Then I go a bit on question 16. Okay, now page 16, question 1. So if you go to page 16, question 1, now three wires exert a horizontal force on a vertical pole as shown. Which vector diagram shows the resultant force R acting on the pole? Okay, now this one you have three different forces. 1, 2, 3. So as I mentioned to you, when you want to produce a vector diagram that in turn shows you the resultant, the first thing you do is you try to draw the vectors from head to tail. Okay, following this rule here in general. Under your notes, page, page 7. You draw the vectors from head to tail. Any gap is the resultant. The direction will be given from the first point to the last point. So if you look at this question right now, you try to see which vector is actually drawn from head to tail. The order won't matter. The order in which they are drawn won't matter. You can draw this one first, you can draw this one first, or you can draw this one first. But the main thing is that they must be from head to tail. So the one that seems to be drawn from head to tail, following all the directions that is shown here, seems to be this one, right? Let me just use a different color to represent it. This one is this one. This one is this one. And then this one is this one. You see, these are all drawn from head to tail. Okay. So notice that this would be my gap. So this one must be my resultant. But is it in the correct direction? You look at this one here. This one should be my first point. This one would be my last point. So I mentioned that the direction will always be from first point to last point. It is pointing in the correct direction. So the answer for this should be B. Now, for the other answer choices, what is actually wrong with them? For answer choice A, you notice that this is wrong direction. It's on the opposite direction of the diagram here. Same goes for C. This one is in the wrong direction. D is also in the wrong direction for the vectors that I indicated here to you. So answer is just B. Okay, this is June 16, P11. Let me just have a look at the answer for you here. Yeah, answer for this is B. It's not showing correctly. Okay, yeah, answer is B. It's just like the diagram is just showing correctly here for you right now. Okay, so answer for that is B. Then after that, let me just go to another one. If you look at question 27, okay, now, is this one of the questions that you didn't know how to do?
No, I could do this one.
Oh, okay. Right, but let me just go through this with you first. Then after that, we'll take a short break. Okay, now this one, question 27, page 27, question 2. There are two forces that act on a circular disc as shown. Which diagram shows the line of action of the resultant force? Okay. Now, this one here is actually kind of like the last example just now that I showed you. Now, you want to find the resultant force of these two. You will know that if this one is 4 Newton, this one is going to be 3 Newton. You draw them from head to tail. 4 Newton, then 3 Newton. You're going to get this as your resultant. Since this is a right angle triangle, you can use Pythagoras theorem. You know that it is 5 Newton. Okay, so this one is fine. You know that to find resultant, your resultant is actually square root of 3 square plus 4 square, giving you 5. Okay. Now, but the question then is, where should it be acting? You see, they give you a few different choices, either here, either here, either here, or either here, right? Now, remember I told you that where your resultant would act, it should actually be at your intersection. So you look at the two forces here. This one is the intersection point. Okay, this one is the intersection of the line of action. So therefore, resultant acts here. Okay, but then you have a new problem already because you see that when it comes to this point here where you say that the resultant is acting, you actually have two answer choices, either answer A or either answer B. Both are showing something similar. But you notice that this angle here is slightly different from this angle here. So which one is the correct one? Okay, now this one, you can see that over here the angle is more than 45 degrees. This one, the angle is about 45 degrees like that. All right. Now, so right now what you can do is you can try and roughly guess what is the angle here actually supposed to be. Okay, this one doesn't seem, I mean, if I try to find the angle, let me just write here. To find angle, let me erase this. Okay, this one. To find the angle, you have this one here, where this one is your resultant. This one is 4 Newton, this one is 3 Newton. What is your angle here? You can say that tangent theta is 3 over 4. Theta is going to be 36.9 degrees. Okay, this is actually slightly below 45 degrees, right? So you look at answer choice A and C. Which one seems to be closest to it? It should be answer choice A, isn't it? The only reason why answer choice B is wrong is because this one is clearly showing the angle is above 45 degrees. What you see here by actually calculating out the angle is that the resultant actually should be at an angle of 36.5 degrees from the horizontal. It is slightly less than 45, which should be this one here. Okay, so this one is answer A. Okay, right, so this one should be okay. Then after that, let me see something else. There's question 40. Okay, right. Do you want to take a short 10 minutes break? You can just answer me in the chat because I think the voice from your side is a bit soft. I probably can't hear you over the sound of the heavy rain and thunder right now. You want to take a short 10 minutes break or should I continue? Okay, right. So we continue or we take a rest? Oh, okay. You want to continue? All right, sure, no problem. Okay, now, okay, let me have a look at question. If you look at page 40, okay, page 40, have you done it? Do you have any problems with that? I mean, what is a scalar? Scalar is just, what is meant by scalar and vector? Okay, okay, now, if you don't have any problems with that, can you just tell me what were the questions that you had problems with? Maybe I try to address that directly first before I continue. Just tell me on the, just write for me on the chat, what question was it? Page what, question what? Page 6. Okay, page 6. Question 1. Okay. Page 6, question 1. Okay, so let me address that one. Page 6, question 1. A, B, C. Question D was okay. All right. Okay, right. So let's go through this one. Okay, page 6, question 1. Now, distance between the sun and the earth is 1.5 times 10 power 11 meters. Take this distance in gigameter. So distance here is 1.5 times 10 power 11 meter. Okay. So you want to change to gigameter. Giga, the conversion or the multiplication factor is 10 power 9. So I mentioned to you before in the notes, if you're converting from non-prefix to having a prefix, you normally just divide. But let me see where it is. It's under page. Yeah, it's under page 4. From non-prefix to prefix, you normally divide. So what I mean by that is this: if you're going from here to gigameter, this one you need to divide by 10 power 9 because you're going from non-prefix to having a prefix. So this one will be 1.5 times 10 power 11 divided by 10 power 9 gigameter. So you should be getting 150 gigameter. One common thing that some students used to remember this is this. They normally see that, oh, if it's for some students, their line of reasoning is this. If they see the thing already has a prefix here, when you want to convert to a when you want to get rid of the prefix, you're just subbing in 10 power 9. Let's just say, for example, I give you this one, 1.5 times 10 power 11. Maybe I give you a different one. Say I give you 25 kilometer. Okay, this one is the prefix. For some students, how they understand things was that, okay, this one is a prefix. I want to get rid of this prefix. I know that this one is equals to 10 power 3. So this one will just be 25 times 10 power 3 meter. So anything else that is not replacing or subbing out the prefix would be divide. That's how some people remember it. Because when I write it like this, uh, some may have problem trying to understand or remember it like that. The easiest way I can tell you is this lah. If you see that your unit already has a prefix and you want to get rid of it, it's as simple as you just subbing in the value for that prefix, giving you this. But if it's something there with no prefix and you want to get it with prefix, you just divide. Okay, some people find it easier to remember in that way. If you want to get rid of the prefix, just sub in the values and it's gone. But if you want to get back the prefix, we just divide. Okay, that's how some of them remember it. So that one is okay. This is part A. All right. Okay, so this one the distance will be 150 gigameters. Okay, and then the other one, the distance from the center of the Earth to a satellite above the equator is 42.3 megameter. The radius of the Earth is 6,380 kilometer. A microwave signal is sent from a point on the Earth directly below the satellite. Calculate the time taken for the microwave signal to travel to the satellite and back. Okay, now this one here requires you to know something from waves. Right? Now, you will have learned from waves right now that microwaves is actually EM radiation. All right, EM radiation has a speed of 3 times 10 power 8 meter per second. Okay, this one requires you to know something about microwaves, which is actually EM radiation. It has a speed of 3 times 10 power 8 meter per second. So right now what they want is you find the time taken for microwave signal to travel to the satellite and back. So to visualize it, what you do is, this is the Earth, this is the satellite. So they told you that the distance from the center of the Earth to the satellite above the equator is this one. The radius of the Earth is 6,380 kilometers. Okay, find the time taken for the microwave signal to travel to the satellite and back. Now you see, the question here says your microwave signal is sent from a point on the Earth directly below the satellite. Now what you have here is this. They tell you distance from the center of the Earth to the satellite is this one. This one is 42.3 megameter. Now, as I mentioned to you, you want to get rid of the prefix, you just it's like you subbing in the value. So this one is 42.3 times 10 power 6 meter. Mega is equals to 10 power 6. Okay. Now, they tell you that you're sending your signal from a point on the Earth. You're not sending from the center of the Earth. Okay, you are sending from a point on the Earth. So that means you are sending it somewhere here. Right? You are sending it somewhere here. At this point here. So what you want to do is to find the time taken for the microwave signal to travel to the satellite and back from a point on the Earth. Means you want to find this one. Okay. The time for you to go here and then here. This is the time that you want to find. Right? You are sending from this point. Okay, on the surface. You're sending from the surface, not from the center of the Earth. So right now, what you need to do is you use this. Okay, now you need to find out what is this distance first. You do know that your question told you that your radius of the Earth is 6,380 kilometers. Your R is 6,380 kilometers. Yes, just minus, which is 6,380 times 10 power 3 meters. So again, you want to get rid of the prefix, just suck in the value. Okay. So right now your distance D is actually just 42.3 times 10 power 6 minus 6,380 times 10 power 3. Okay. Then you should get the answer. What's the distance? 42.3 times 10 power 6 minus 6,380 times 10 power 2. Then you will get the answer as 35.9 times 10 power 6 meter. Okay. Now then after that, you want to find the time, right? Oops, sorry. Okay. You want to find the time, you need to use this. V is distance over time. Time is distance over V. So to find the time, you need to take the total distance divided by your speed. Now notice that you are traveling twice the distance. This distance D here is 35.9 times 10 power 6. When you travel to the satellite and then back, you're traveling twice the distance. So your distance travel is actually 2 times. And then you divide by your speed of your microwave, which is EM radiation. You will get your answer as this. 35.9 times 10 power 6 times 2 divided by 3 divided by 10 power 8. You should get the answer as 0.239 seconds. Okay. Wait, let me just rewrite it. 0.239 seconds. Okay. Right. One thing here I should probably mention to you here is that final answer SF is usually minimum 2 SF, maximum 3 SF. Okay. If you put 1 SF for your answers, your examiner will minus mark. If you put 4 SF for your answers, your examiners will also minus marks. Okay, so minimum is 2, maximum is 3, right? So let me see this one first. Let me check the answer. Region 15P23. Open up the answer. Region 15P23, question 1. Yeah, 150 gigameter and then 0.24 seconds or 0.239 seconds from what you found here. All right. Then after that, if you're okay with that, then you have part C, right? Okay, so are you okay with part B? Okay, right. So part B is okay. Yeah. Sometimes like for questions B, it helps if you try to draw out to visualize what is happening. The answers would then make more sense to you. Okay. So if anything, yeah, this one I think maybe you should just write times 2 because traveling twice the distance. Okay. All right, part C. Speed v of a sound wave through a gas or density rho and pressure P is given by this, where C is a constant. Show that C has no units. Okay, now this one here, I'll write it on the right hand side of the board here. Okay. Show that C has no units. In a way, it is similar to your example, but let's go through that. Okay, now V is square root of Cp over rho. You get rid of the square root there, you get V square Cp over rho. Okay, so you make C the subject, so you get rho V square over P. Then after that, the unit of C is the unit of rho V square over unit of pressure. Now, you need to find out what is the unit of pressure first. Okay, wait, let me see whether I'm doing things correctly. Rho V square over P, yeah, correct. Okay, now find out what is the unit of pressure first. Pressure, let me use a different color for you. This one, pressure is actually force over area. So unit of pressure is unit of force over unit of area. This one will be kg meter per second square because it's mass times acceleration. This one is meter square. So you get kg meter negative 1 second negative 2. Okay. So then from here you can start to proceed. Unit of density is kg per meter cube. Unit of speed or velocity is meter per second square. Then divide by this one, we have kg meter negative 1 second negative 2. So you try to simplify the top part first. You get kg, then you get meter negative 1. Then you get second negative 2. The bottom one will be kg meter negative 1 second negative 2 also. You try to simplify it further, you will notice that you get kg power 0, meter power 0, second power 0. So therefore, no units. Okay, so this is one way to go about in getting the answer. Right, so part D, you mentioned that you are okay with that, right? So is there anything else on that that you need to sort out? If not, then maybe I can just give you some other examples to do. Okay, can, no worries. Page 11, 1B. Ah, also showing the unit. Okay, so let me just clear this thing off. All right. Okay, you have a beam that's clamped at one end of an object X. A beam is clamped at one end and an object X is attached to the other end of the beam as shown. The object X is made to oscillate vertically. The time period of oscillation is given by this, where M is the mass of X, L is the length between the clamp, E is the Young's modulus. So the Young's modulus of this is this. Okay. Yeah, that's why I think I know why. Okay. Now Young's modulus is a new is another physical quantity, but you will learn it under chapter 7, deformation of solids. I think I know why. Because you try to find from this equation, but then you get stuck in K. What is the unit of K, right? They never say, right? Okay, the thing here is this. You are not supposed to try to find the Young's modulus, the SI based units for Young's modulus from this equation, because K here, you do not know what is the units. The way to go about this was that with the assumption that you have completed the syllabus, then was that they said that you should have known that E, Young's modulus, is actually stress over strain, which is actually force over area. Let me just put this down for you, which is actually force over area and then change in length over original length. So you get F L A. Let me just give you this. C, okay, F L A E. Okay, let me just. Okay, now this one, let me just write it down properly for you. Stress is, this one is called stress. Okay, it's defined as force over area. You notice that it's somewhat similar to pressure, the definition, but you will learn this in chapter 7 later. Okay, so unit of stress is unit of force over unit of area, which in turn is kg meter per second square divided by meter square, giving you kg meter negative 1 second negative 2. And then strain, this one is called strain. You will learn later also. Strain is extension over length. This is extension over original length. So from here, the unit of strain is the unit of extension over unit of length, which will be meter over meter. Meter power 0, no units. Then from here, Young's modulus is stress over strain. So unit of E is unit of stress over unit of strain. So this one would just be kg meter negative 1 second negative 2. This one has no units. Therefore, it's kg meter negative 1 second negative 2. Sure. Okay. Right. This one is this. So yeah, this one here, my guess is that you try to find from here and then you got stuck. The K here is not your spring constant or anything, it's just some other random constant. So from there you might have gotten it gone another way. The proper way to do this is this. It is subject to you knowing what is Young's modulus. Okay? Right? So the next part should be okay. So anything else on that? Okay, right. So if you're okay with that, then let me just try and ask you some, let you do some question. Okay, now can you, this one is more on vector diagrams again, asking you to interpret vector diagrams. Can you just look at page 28? Okay. Okay. Just have a look at page 28. Let me just rewrite this for you. Page 28, question 2. Now the diagram here shows two vectors x and y. The vectors are perpendicular to one another. What is the magnitude and direction of vector x minus y? Okay, now this one here, I need to kind of explain to you again something else. Okay, now, do you recall that in the examples in the notes, I gave you vector A, and then I gave you vector B, and then I told you that if you want to find the resultant, it is the same as you drawing it from head to tail, like this. Let me just erase this one. I mentioned to you that it's the same as you drawing it from head to tail like this. Vector A, vector B, and then eventually your resultant is this one. Okay, so this one, I told you this one was your first point. This one was your last point. Okay, this one is you trying to deduce out what is your resultant from the vector diagram. This is your vector diagram. Now, the one thing I didn't really mention to you yet was this. In vector equation form, this one is actually vector A. In vector equation form, I emphasize the word vector equation form, not your normal equation, but vector equation. This diagram in vector equation form is actually represented as vector A plus vector B equals to your resultant vector. Okay. Now, interpreting this equation, it is telling you vectors A and B drawn from head to tail gives resultant R. Let me write this properly for you. It gives you resultant R. Okay. This, when you see it in vector equation form, vector A plus B equals to R, it means vector A and B drawn from head to tail gives you resultant R. Okay, this one isn't inside your notes. Okay, this isn't inside your notes. Maybe you try to write it somewhere convenient in your notes later on. Okay, because you need to know this in order to be able to do this. All right. Now, okay, so let's just say for this one here, question 2, they tell you the diagram shows two vectors x and y. The vectors are perpendicular to each other. What is the magnitude and direction of vector x minus y? Okay, now the easy way to go about this is to think of it this way. You say let this be let this be R lah. Okay, let this be R. So R, vector R is the same as vector x minus vector y now. Okay, you're basically, what you do now is that you try to represent x minus y as a separate vector. Let this be vector R, which in turn gives me this. What you then do is that you try to rearrange this vector. It becomes vector x equals to Let me use a different color. This one becomes vector r plus with vector y gives me vector x. All right. Now notice that this form of the equation is now the same as this form. This plus something, this vector plus this vector gives me this vector. Now, the way to interpret this one now would be that it's telling you vector r and y drawn from head to tail gives x. Now, so now you try to draw this in the form of a vector diagram. Okay. Now, right now you may be thinking, I don't know r, but I know x and y because it's given here. All right. So now you try to draw it in such a way that it follows this relation now. Okay. What do I mean by that is this. I know vector y is pointing downwards. Okay. Where can I draw this? Or maybe I draw at the top. I know that vector y is pointing downwards like this. And then I know that vector x is going like this. Okay. I know that vector x is going like this, following the directions that I've indicated here. Now, I have an unknown vector r. All right. Now, think of it this way. My vector r could be something here like this. All right. But what should be its direction such that it follows this relation? Notice that here, when you write it in this form, it means vector r and y drawn from head to tail should give me vector x. So you consider the cases here. What if I draw it like this? This one is my vector r. This is not vector y and r drawn from head to tail, right? This is definitely wrong, right? So what about if it is in this direction? This one was still vector x. This one is vector y. How about if vector r is drawn like this? This is r. This is y. And then this is x. So now notice that if my vector r is in this direction, I can say that r and y drawn from head to tail gives me x. Can you can you roughly get the concept here? What I'm basically trying to do is that I am trying to work out by trial and error how the diagram would look like such that it tells me this, such that I know that if this vector drawn with these two vectors drawn head to tail will give me this. Okay, so right now, basically, to just recap a little, whatever you get here, x minus y, you just represent it as a separate vector. Okay, and then after that, you try to change it in a form such that is something plus something equals to something. When it's in that form, it will mean that these two vectors drawn from head to tail will give me this resultant here. Okay, so from there, you try to see from the existing vectors that are given to you, you try to draw it out, and then you try to see that missing vector. How should it be drawn such that it is actually drawn head to tail with r and y to give you x? So in this case here, you will notice that drawing it this way, like the diagram on the left, is wrong. This one is not head to tail. But drawing it in this direction would be showing that it's from head to tail. So it will be correct to say that if it's in this form, vector r plus vector y is equals to vector x. All right. So now you want to find the magnitude and direction of vector x minus y, which is your r here. Okay, so from here, what you can do is you want to find the magnitude. Recall that I mentioned to you that right angle triangles, you normally can just do your calculation straight. So this one is 8 Newton. This one is 6 Newton. Your R is your hypotenuse. You can say that R is the square root of 8 square plus 6 square, giving you 10 Newton. And then your angle would be this one. So you will say tangent theta is 6 over 8, giving you an angle of 37. Okay, it's 36.9 by running out to 37 degrees. So right now, what is the magnitude and direction of vector x and y? It will be 10 Newton. Okay, either answer choice A or B. But at an angle of 37 degrees downwards from direction x or 37 degrees upwards from direction x. You can see from here, this one is your vector x. It's actually 37 degrees outwards from your direction of x. So the answer is B. Okay, this is June 17P13. Let me double check the answer with you. June 17P13 should be question 2. Yeah, the answer is B. Okay, so this is one way of doing this. There's another one that you can try. This one would be question 22. Is it 22? No, not this one. Do I have 19? Okay, right. Try and have a look at page 19. Okay, let me just clear all this one. Page 19, question 3. Vector P and Q are drawn to scale. Which diagram represents vector P minus Q? So in some cases, for your exam questions, they do come out questions like this. They always like to throw something in where something is minus something, and then they ask you to find out what is the vector that represents this. So like this one, I show you again the method. This one P minus Q, just let it be some random vector value. Let's just say let R, let it be equal to R lah. Okay. This one assume as R. So here you will say that R is equals to P minus Q. So you try to rearrange it in one form such that is plus something gives you something. So this one is vector R plus vector Q equals vector P. So this in turn tells me vector R and Q drawn from head to tail gives P. So from here, you want to find some this relation. You look at all these like possible vectors here. Which one in which direction will actually tell me this relation? You can do try and error here. Okay. So the simplest way I normally find is you trying to draw these two vectors first, the ones that are already given to you. Okay. So say right now, vector P is this. Then vector Q is something like this. you're probably looking at something along the lines like this. But the question is it going this way or is it going this way? So you have to see from here then. R plus Q equals P. That means R and Q drawn from head to tail would give me P. So this one here is actually my R. Okay, but which one is the correct direction? If I say it is like this, you see the arrowhead of Q meets the arrowhead of R. The head is meeting the head. So this one is definitely not head to tail already. This one is out. But if I draw it in this direction, you'll notice that the head of Q is meeting the tail of R. This one is drawn head to tail. So this one drawn head to tail right now is giving me P. Okay. Oh wait, maybe this one. Okay, this one is it correct to say so? There's something about the direction. This one is, but this one doesn't seem to be correct also, right? Because this one is my first point. This one is my last point. Yeah, if it's like this one is going from my last point to my first point, right? This doesn't seem to be correct also. So what you can do is you do something like this. What if your P is like this? P is like this, but your Q is like this. Wait, am I doing this? Oh, sorry. I still maintain my P, but this time I say that my Q is like this. So this will be my R. So same thing as before. Either is this direction or this direction. If I consider it as going in this direction, I will notice that it's from head to tail. And then this one is from my first point, and then this one is to my last point. It is actually showing me this relation, isn't it? So the answer should actually be C then. Because you see, there are like two different answer choices, right? You see, if I use this first one here right now, although this one I can estimate it as being drawn from head to tail, something doesn't seem right about this direction here, because you see, this one being my first point and this one being my last point, by right, the P should be pointing here, but it's pointing opposite. So this one is not correct. Okay, so let me just write this one here. This one is direction incorrect. But this one is head to tail. This one is correct. But the direction here is this incorrect. Whereas this one, the second one that I did here, this one is head to tail. This is correct. And then from first point to last point, direction is correct also. So it's telling me this one. The answer should be C. Okay. So it's something like try and error. Okay. You roughly get the concept, right? It's something like guesswork now. You're trying to guess which one is telling you this story for the equation, right? So this one is for zero. Let me just double check the answer for June 16 P13. Okay, June 16 P13. This one was the answer. Yeah, the answer is C. Okay, the answer is C. Right, so just be mindful a bit about this. So this one, let me just cancel it off. This one was correct. This one was wrong. Okay, so that one is okay. So then let me see another one. There's actually two more examples that I think I should go through with you. Okay. Okay, 61. Okay, now 61, page 61, this one, question 3. Question 3. You can try and do this later as your homework. Okay, page 61, question 3, which is this one. It's something similar again. But this time they tell you specifically what is x minus x equals to p minus r. So this one I will ask you again probably next week, whether you manage to get the answer following what I just taught you. But then now I go through two other separate questions for you. It's more like looking at diagrams to see whether you really get it. Okay, now there's another one. This is question then page 22. All right, just have a look at page 22. Okay, page 61, do as your homework. Just have a look at page 22. Okay, now they tell you an arrow, again, question 3. They tell you that an aeroplane can fly at a velocity of x when moving through still air. When flying in wind, the airplane's velocity relative to the ground is y. Which vector diagram shows the magnitude and direction of the wind velocity w? Okay. Now this one is this aeroplane is flying with velocity x when moving through still air. But when it encounters wind, it's now flying with velocity y. This is kind of like the resultant velocity. Okay. You first have velocity x of your aeroplane when it is under still air, moving in still air. It then encounters wind with velocity w. When the aeroplane with velocity x encounters wind with velocity w, its velocity now becomes y. Basically, it's something like this now. Velocity x of the aeroplane, once it meets velocity w of the wind, is now flying with a resultant of y. Okay. So basically, the question now is asking you which of this diagram is correctly showing the direction of the wind velocity w. You're basically trying to find any one of these equations that is showing you this. But let me just write it here like this now. You know, some explanation here. When playing with velocity x, when playing with velocity x encounters wind with velocity y, is velocity is resultant velocity is y. Okay. Oh, sorry, wind velocity W, right? Sorry, my typo error here. Basically, what it's telling you here is this. When plane with velocity x encounters wind with velocity w, its resultant velocity becomes y. Okay? Its resultant velocity becomes y. So which in turn gives you this equation, x plus w equals to y. All right. So same thing as before. Vector x and w drawn from head to tail gives y. So try and see from these diagrams here, which one is telling you that. Can you just maybe give me an answer? Just type in the chat A, B, C, or D. X and W drawn from head to tail gives you velocity Y. Gives you Y. Okay, so let's just see from there. Okay, head to tail, right? We say X and W drawn from head to tail. Now look at X and W. You can just try and single out the point where they meet to see whether they're drawn from head to tail. You look at this one here, for velocity X and W. Notice that the tail is meeting the tail, right? So this is not head to tail. This is not head to tail. For head to tail, the head must be meeting the tail of the other. That is what I always mean by head to tail. If you see head meeting head, tail meeting tail, it is definitely not correct. So like here, you see, yes, you are correct in saying that it should be A. You see now, if I look at velocity W and Y, sorry, X and W, I look at the point where they meet. You see now this is the head, and then this is the tail. The head meeting the tail, head to tail. All right, but you see the others, like this one, X and W, this one and this one. Notice that tail is meeting tail, tail is again meeting tail. So this one is always tail and tail. This one is always tail and tail. This is also tail and tail. When meeting head to tail, you will see that head and tail will meet. Okay, that is what we mean by head to tail. So now you see, drawn from head to tail, this is correct. Then this one here probably is your first point. This one you can see clearly is your first point. This one is your last point. So from first point to last point, it should be going here, which is what you're seeing here. So this is correct. This is showing you this, right? So this is what we mean by interpreting it. So that's why I say, that's why you notice that when it comes to interpreting those little diagrams like you've been doing here, the concept of head to tail is actually really important. Your teacher might have taught you a different method, but I would say that normally just by referring to the concept of head to tail is actually easier. It makes your life a lot easier rather than trying to think of the different directions. Okay, right, just one last question. It relates to resolution of factors in diagram format. There's one particular question that I think is a good question to try. What is it? Page 2. Yeah, now I remember. It's page 2. Try and have a look at page 2. Okay. Okay. Now the arrow represents vector R. Which of the following diagram cannot represent R as two perpendicular vector? Okay, the keyword does not represent R as two perpendicular vectors. Now, this one here is asking you which of, basically what you have here are the vector components. Sorry, my handwriting is really bad. Okay, they tell you right now, you have a vector R. Okay, you have a vector R right now. All right, this vector, as I mentioned to you earlier in the notes when I talked to you about resolution of vectors, any vectors can be resolved into two perpendicular components such that they will combine together to produce back your original vector. Okay, so the part here is that the question is asking you, out of these possible vector components choices, which one actually won't give you back this one? That is what the question is asking. Which of these vector component combinations will not give you back R? To give you a better idea of that, recall that just now I told you if they are vector components, if you try to draw them from head to tail, they will give you back the original vector. So what you want to do now is you try to rearrange each of these vectors from head to tail and see whether they give you back the original vector. What I mean by that is this. Let's just say for answer choice A, you try to shift this to this side. It's drawn from head to tail, right? Your resultant should be something like this. Okay. And then if you talk about the answer choice B, you try to shift it this way so that it's drawn from head to tail. You notice that your resultant should be like this. The gap will always be your resultant. The direction is always from your first point to your last point. Okay, you always make use of that rule. You'll be able to determine the direction of the resultant easily. Then now you look at answer choice C. You try to shift one of the vectors around so that it becomes head to tail. You will notice that this one, the resultant is like this. This one here being your first point. This one here being your last point. Okay. And then for this one, the answer choice D, you shift one of them so that they form head to tail like this. The resultant would be this one. Again, this one is your first. This one is your last. So now, which one do you think now does not represent R as two perpendicular components? Which one here, which does, when combined together, doesn't give you back the original vector R? Should be C, right? Okay, you see, wait, this vector plus this vector will give you this, right? Isn't this the same as this? All right. Then if you see for B, this vector plus this vector will again give you this vector. This also seems similar to this, right? Right? Then after that, you see for D, this vector plus this vector will give you back this, right? You see this again is the same as this. But if you see for C, this vector plus this vector will give you this. This one is nowhere similar, right? Nowhere similar, right? So these two, when combined together, doesn't give you back the original vector. Okay, that's why we will say that the answer here is actually C. Okay, which of this diagram doesn't represent R as two perpendicular components? Basically, they're asking you if this one I resolve it into two perpendicular components, which one here doesn't give me back the original one? C actually doesn't give me back the original one, but A, B, and D, they will give me back the original vector. C doesn't. That's what we need. Okay, right? So far, so good.